All right, today we're jumping into a really clever idea that's, at the very heart of our digital world. We're going to talk about how we find similar things when you're dealing with just these massive, massive oceans of data.
I mean, think about it. You've probably done this 1,000 times. You use Google's search by image, or maybe Spotify recommends a song that just has that vibe? How in the world does that actually work? I mean, seriously. Comparing what you're looking for to every single item out there one by one, that would take, well, basically forever. The scale of this problem is just staggering, and there's a name for it: similarity search.
So let's be clear, the main challenge here isn't about finding an exact copy. Nope, that's actually the easy part for a computer. The real magic, the tricky part, is finding things that are just near each other. Stuff that's visually similar, or sounds similar, or even just reads in a similar way.
Yeah, your computer is an absolute champion at exact matching. Give it a specific file name, a specific line of text, and bam, it finds it instantly. But asking it to find a photo that kind of looks like another one, that's a whole different ballgame. For a machine, this whole concept of similarity is super fuzzy and complicated. And that brute force method we talked about, comparing everything to everything else, just forget it. It's completely impossible when you're talking about billions of files. No way.
So, to tackle this massive problem, computer scientists looked at a standard tool they had, something called hashing. But, and this is where it gets really interesting, they decided to use it in a way it was never designed for. In fact, they decided they were going to break the #1 rule of hashing.
Okay, so what you're seeing here is a complete 180 on a core computer science rule. On one side, you have conventional hashing. This is what's used for things like password security, and it is totally obsessed with avoiding what are called collisions. The whole point is that every unique thing gets its own unique digital fingerprint, no overlap. But then you have locality-sensitive hashing, or LSH, and it just flips that script completely. Its entire goal is to encourage collisions, but, and this is the key, only for items that are already similar. The whole idea is that if two things are alike, they should end up with the exact same fingerprint.
And this totally counterintuitive idea, actively seeking out collisions instead of running away from them, well, that's the breakthrough. That is what makes lightning-fast similarity search possible. Okay, the absolute best way to get your head around this is with a library analogy. So, picture this. Every single book has a super specific, unique code on its spine. Finding one exact book? Super easy, right? But finding all the books that are like it? Oh, that's a total nightmare. Now, what if you did something different? What if you just threw all the sci-fi books onto one big shelf and all the mystery books onto another? All of a sudden, similar books are all grouped together. They've collided on the same shelf, and that is exactly what LSH does. It creates these big, broad digital buckets instead of shelves.
So let's put a formal definition on it. Locality-sensitive hashing, or LSH, is basically a technique that hashes similar things into the same digital buckets with a high probability. Now that last part is super important, with high probability. It's not a perfect system, okay? It's an approximation, but it's an incredibly fast and effective one. Instead of searching through billions of items, you now only have to search inside one tiny, highly relevant bucket. It's a game changer.
Okay, so how does the algorithm actually create these buckets? It sounds like magic, but it's not. Let's take a quick peek under the hood at one really simple but powerful method. So one of the most popular ways to do this is called random projection. And the name itself actually gives you a pretty big clue about how it works. The core idea is surprisingly simple, but trust me, it's powerful. You can basically figure out if two things are close to each other by looking at their shadows. Just imagine all your data points, let's say they're images, are just scattered around in a big space. What random projection does is it just draws a random line straight through that space. That's it. Everything on one side of the line, we'll call that bucket A. Everything on the other side, bucket B. The logic here is just beautiful in its simplicity. If 2 points are already close together, they are very, very likely to land on the same side of that random line. And you don't just do this once. You repeat this process with a bunch of different random lines. And by doing that, you create a really reliable digital signature that groups similar items together fast.
Okay, so that's the abstract idea. But how does this translate into stuff we actually use every single day? Because this isn't just some concept in a textbook. It is the engine running behind some of the most impressive features in modern technology.
LSH is the magic behind that reverse image search you use. It's how an app like Shazam can hear a song in a loud bar and tell you exactly what it is. It's creating an audio fingerprint. It's used all over the web to find duplicate content, whether that's spam emails or plagiarized papers. It's even used in computer security to spot new malware that's just a tiny bit different from a known virus. It's everywhere.
And if we look right here at the source material, you can see just how wide-ranging these applications really are. It's not just images and music. We're talking about fields like genomics, where it's used to analyze gene similarity, and even in digital video fingerprinting. The list just goes on, which shows you how this one core idea has just exploded into dozens of different fields.
So what's the big takeaway here? It's that LSH really embodies a powerful philosophy for the world we live in now. In the world of big data, clever approximation often beats slow perfection. I mean, when you're dealing with billions or even trillions of data points, searching for that one single perfect answer, it's just too slow to be useful. A really, really good answer that you can get almost instantly, that is so much more valuable.
And that kind of leaves us with a final thought, right? This whole principle of accepting a smart approximation to get massive gains in speed, that's not just a computer science trick. It's really a strategy for dealing with overwhelming complexity in general. So the question is, where else in our lives is being good enough the perfect answer? Where else does it pay to be clever and fast instead of perfect and slow?